Hello there. Time to start problem 2. This first part seems to be trivial manipulation. In this case, alpha to minus first lies in, that was wrong. We have a gamma in gamma mark S, and then alpha, gamma, alpha to minus first of S equals S. My God. This is really silly. If we have such a gamma, then we shall prove that the right-hand side is true, so that this is a subset of that. And we just do that, gamma alpha to minus first of infinity. This was S, and gamma S equals S, so it's alpha S, which is infinity. And so that proves the inclusion this way. No, that was what we should. Yeah, we have to assume then that alpha of some gamma, alpha to minus first of infinity equals infinity, and then work out that gamma lies in this set. We have to do the other way as well. This was alpha to minus first of infinity. That's S, and we operate on alpha, the inverse of alpha on both sides. So we get S, so that proves that way. Right. I would rather yeah, so we work on this. So given an element in gamma mark, then we see how it operates at infinity. So we have that alpha gamma mark alpha inverse of infinity equals infinity. and which elements map infinity to infinity. And if C is distinct from naught, then infinity maps to A divided by C, which is a rational number. So it can only map to infinity if C is naught. And then AD is unity, and the only units among the integers are plus minus 1. And of course B is an integer. So by doing this, it's equivalent to a group mapping infinity to itself. And what do we have possibilities here? If A and D is unity, then it's some power of T. So it could be plus minus some power of T's. That's the possibilities. The structure of this group, let's find the minimal positive n being in the group. Or could we just map it, make a homomorphism to n? So we have a homomorphism into the integers, and there all ideals are principal ideals, so there's a minimal guy here, simply. So there's a minimal positive guy, and that's of course the maximal negative guy, and then n equals naught we have. And that means the generator can be T to some power. Oh, that should be an H. The ramification index, I believe, yeah. And it can be minus T to the H or plus minus T to H. Of course, we have T to nth lies in gamma of n, which means that h must divide n. That's the last thing we should show. I did read the problem, so when I read the problem I immediately thought, well, it must be a divisor of n, so that's why my thoughts were ahead of this point. Well, and then we are through with B. Oh yeah, that's true. It might depend on alpha. That didn't occur to me. well, let's write up the formulas. If we have alpha to minus first infinity equals beta to minus first of infinity, so we have chosen another guy. That means that beta alpha to minus first maps infinity to infinity. So this lies in t to the nth. T to some power. So alpha minus first, that's t to the nth beta, t to x, I said beta, didn't I? And alpha equals equals t to minus nth beta we must multiply with beta from the left, so they are the opposite direction. Alpha to minus first, that's beta t to the nth. And t to the minus nth here, so we end up with the same power of t. That was the first part. The gamma mark equivalence class of S, that is if we change S with another point, gamma mark of S call it T, and then do the same the guy that maps t to infinity then instead of alpha we must use the new alpha. This is silly. I'd rather do it the other way. S equals gamma mark t, then alpha to minus first S alpha equals alpha to minus first gamma mark t alpha. This actually requires some thought. If we can write any other guy, alpha beta, beta to minus first alpha, that doesn't change it. But if it's beta alpha, then it's alpha to the minus first, beta to minus first, and then this one is expressed the same way, but then we have beta minus first and beta to the right, beta minus first to the left and beta to the right. So the inside should be exactly the same. Do I need to write that? I don't think. I'll just write it. Was that it? No, it was the other way around. S equals gamma mark S mark. And then we put that in. And then we should be home. Time for a break. Hello, I've had my break. It's 5 o'clock in the afternoon, and you may be able to see in the curtain out there that it's pitch dark outside. Approaching winter really quick. I checked this idea and it worked. And then it occurred to me that I need to show that this contains more than the unit element, with n being equal to naught. Isn't it an m here and an n there? Well, it should be n both places. But we can actually use t to the nth here. This actually lies in gamma modulo n. We work equivalent classes modulo n. So this is the unit matrix, and then modulo n, this becomes the unit matrix, which is the definition of gamma of n, meaning that this guy gives a non-trivial element here. And then we can start on the next part of the problem. Well, we choose n equals to 1, and then we do what? Studying the section, I actually tried to make the expansion at another cusp of one of the functions, and that gave me the idea I'm going to use now. We multiply by the inverse of alpha from the right. We use the transitivity. And f lies in nk of gamma mark, so that means this equals f itself. And this is good because that's what we are going to say something about. And we go to the other side. And it's all k. There we go. That means we have a function, and when we operate on it with t to h, it's invariant. And we know that it has the expansion f of z has the form alpha is not a good one here. an q n to nth. Now let's apply Tn to that. T to h. And then Z is displayed H. This gives Q to nth. But we have this. This factor, which must be equal to unity for this equality to hold. Meaning that nh divided by capital N must be integers if an is distinct from naught, which implies that n equals n divided by h. Not really times an integer. So we sum over I instead. An. Oh, then we need to write the power here. E to 2pi. N was capital N divided by k. Oh, we should call it j instead. Divided by h. That was a surprise. I really had no idea where that h came from. So only powers of QH occurs. Where minuscule n is given by this expression. All right. And the others vanish, of course. Surprise. What does a minus mean? I just skipped the minus. I put the minus over to t to h, claiming in my head, without stating it, that the minus meant nothing. But if k is odd, we should have a change. If k is odd and h is odd, then we should have a change of sign. No, it's now let's just check the first page here. I have no idea why this doesn't work, the trick doesn't work in this case. it appears that we need an even n for stuff to work out. But we do not here. That's really weird. Anyway, it's time to start cooking too. So I'll leave you here. After dinner, I looked at the problem again, and it became obvious how to solve part D. And then it turned out that E was quite easy as well. Unfortunately, the recording, either it was lost or I didn't record it all, I don't know. So I'll just explain what I did. Now in A we had the problem of getting rid of the plus minus, the two possibilities. And it's actually in this case minus, the identity lies in the group, which means that it can just be absorbed at gamma mark, because minus gamma mark is still in the group. So we don't need to take care of any signs. No problem with any signs here. Then in part E, when we do this operation, we get minus 1 to kth. I missed that at first. That means if k is even, then we just get the expression I already had in black. So it's just a question of extending by 2, and then we only get the even powers, of course. Now in case k is odd, then we get a minus here. And that means that the additional power here must be minus 1 in order to give the same. That implies that h or nh divided by n must be 1/2 plus some integer, which we call j. And at this point it occurred to me, oh, that explains everything. Extending this by 2, we get 2j plus 1/2. So this gives the odd numbers divided by 2h. So that's the only powers which occur.